This is the first of two lectures about what's called the Fibonacci sequence. I'll tell you what that is very shortly, but I first want to think about taking the numbers that we got out of the train problem and arranging them in a list with commas in between. I want to write T1, T2, T3, T4, T5, and so on with commas in between. In other words, I want to write 0, 1, 1, 2, 3, 5, 8, 13. If I do this, I'm going to call what I get a sequence. And the individual numbers in the sequence are called terms. For example, the fifth term of the sequence, that is to say the term in position number 5, is 3. Now we generated that sequence, or we saw that we could generate that sequence by using a certain formula which said that Tn equals Tn minus 2 plus Tn minus 1. It said that you can get a term of this sequence by adding the previous two terms. Now this is an example of what is called a recursive formula. That is to say, a formula that computes a term of the sequence by using prior terms. Now note that the formula is not enough to specify the sequence. If I said to you, well, here's a recursive formula, please tell me the sequence. Well, you couldn't do that. And the reason is because you couldn't get started, right? You wouldn't know what to use for the beginning of the sequence. It turns out that it's enough just to tell you a little bit more, called base cases. Here it's two base cases. Namely, you say that the first term, T1, is 0, and the second term, T2, is 1. As soon as you know that, then you can generate the entire sequence. You see, then T3 would have to be T1 plus T2, which is 0 plus 1, that's 1, and so on. You can, as soon as you have the base cases written down, you can begin to use the recursive formula. It's like turning a crank, and you can just crank out the entire rest of the sequence. All right, let's look at another example. And this is the example that's called the Fibonacci sequence. You might think that's a pretty unusual word. This is an Italian name, Fibonacci. Now, for this sequence, I'm again going to specify two base cases. This time I'll say that the first term, f1, is 1, and the second term, f2, is 1. I'm using f now instead of t because, well, it's Fibonacci sequence. The recursive formula looks just the same as before, except for the fact that I'm using the letter f instead of t. It says that fn equals fn minus 2 plus fn minus 1. Now, let's use it and see what the terms of the sequence begin to look like. You already know f1 is 1, you know f2 is 1, so what would be next? It would be f3. Well, using that recursive formula with n replaced by 3, we get that f3 is f1 plus f2. But we know that f1 and f2 are both 1, so f3 must be 1 plus 1. That's 2. Well, what about f4? Well, if we now apply the recursive formula with n replaced by 4, it says that f4 is f2 plus f3. And f2 we know is 1. What about f3? Well, we don't get it by looking over on the left. What we do is we realize, oh, that's what we computed in the previous line, right? f3 is 2, so we can now insert that information on this line. So f4, which is f2 plus f3, must be 1 plus 2, which is 3. Similarly, f5 is f3 plus f4. That equals 2 plus 3. That gives you 5. f6 is 3 plus 5, which is 8. f7 is 5 plus 8, which is 13, and so on. Once you get the hang of it, you probably think it's an awful lot of writing to write out one line for every term. You can simply write it with the commas in between the terms, as shown below. 1, 1, 2, 3, 5, 8, 13. 8 plus 13 gives 21. 13 plus 21 is 34. 21 plus 34 is 55. And you can continue this as long as you like. Now, it's interesting to note that actually this is the same as the train sequence, except that it doesn't have the 0 at the beginning. So the train sequence went 0, 1, 1, 2, 3, 5, 8, 13, 21. This is exactly the same, except it's missing the 0 at the beginning. Now this sequence is named for an Italian who lived in the 13th century. I won't even attempt to pronounce his full name. Usually none of that is used, and we call him Fibonacci. There's a assumed picture of him. I don't know how accurate that might be. That could have been drawn long after he lived. Anyway, the sequence is named for him, and he really did write about this sequence. Let me also point out that the numbers appearing in his sequence are called Fibonacci numbers. So any number appearing in the sequence is a Fibonacci number. For example, 13 is a Fibonacci number. 14 is not a Fibonacci number. One last example in this lecture, and I'm going to now talk about a different sequence. This one is called the Luca sequence. It looks like Lucas, but in fact it's named for a Frenchman, so we pronounce it in the French manner. It's the Luca sequence. And again, there are two base cases. The first term, L1, is 1. The second term, L2, is 3. The recursive formula again says ln equals ln minus 2 plus ln minus 1. In other words, you get a term of this sequence by adding the previous two terms. So if you do this carefully, you'll discover that L3 is 1 plus 3, which is 4. L4 is 3 plus 4, which is 7. L5 is then 11. L6 is 18. Again, just think you're always just adding two terms to get the next one. So here's how it begins. 1, 3, 4, 7, 11, 18, 29, 47, 76, and so on. Of course, you could continue this as long as you like. This is really a so-called infinite sequence. It's a sequence of numbers that goes on forever.